Good afternoon. Today we're going to discuss more on multi-equation models, except these models are known as simultaneous equation models. And with simultaneous equation models, here we have a slide with modeling approaches, the various structural models. Before we talked about seemingly unrelated regression models, but now the emphasis is going to be on simultaneous equation models. What are we trying to capture here? Well, we're trying to capture not only multi-equation models, but equations that have more than one dependent variable, but the dependent variables are jointly determined. For example, we might have a simple model for a market for a given commodity that involves two equations, a supply and a demand function. And what do we do with those? Well, we determine the equilibrium price and quantity of the commodity in question. And a model is said to constitute a system of simultaneous equations if all of the relationships involved are needed for determining the value of at least one of the endogenous variables. So we're going to have more than one dependent variable, but what we're going to find out is that some dependent variables are going to be on the right-hand side of certain equations. So from the view of statistical inference, the relevant characteristic of simultaneous equation models is the appearance of endogenous variables, just as I said, among the explanatory variables or exogenous or predetermined variables in at least some of the equations. It's hard to come up with a generic representation of simultaneous equation models, but I've attempted to do that here. So in this slide, if you'll note, there are G endogenous variables, Y1, Y2, YG. These are going to be jointly dependent. Notice that the respective endogenous variables for at least some of the equations should have some right-hand side variables that are dependent variables. Now, that doesn't mean in the first equation we need all the other dependent variables, and in the second equation the same. We have to have at least some dependent variables here. The x's constitute a set of explanatory variables, either exogenous or lagged endogenous variables. You could also have lagged exogenous variables. And each equation need not have the same set of explanatory variables in each of the respective equations. And of course, we have the error terms. Now, in some simultaneous equation models, we could have identities which are deterministic. For example, supply equals demand, or in the case of macroeconomic relationships, GDP is equal to personal consumption expenditures plus gross private domestic investment plus government expenditures plus net exports. So the equations in a simultaneous equation model specification could correspond to behavioral relationships, technological relations, or some deterministic, which could be definitions, identities, or equilibrium conditions. And in deterministic equations, the stochastic disturbance terms are identically equal to 0. So there's a lot of structure in a simultaneous equation model. The alternative for simultaneous equation models, at least with the use of time series, is a vector autoregression. But in those cases, explanatory variables typically are replaced by lags of endogenous variables. And in a vector autoregression, it acts more like a seemingly unrelated regression model because there aren't contemporaneous dependent or endogenous variables. Now, a lot of equations, it may be more simple to write the set of equations in a vector matrix form. And if we let the beta matrix here consist of the coefficients associated with endogenous variables, gamma, the coefficients associated with the set of explanatory variables, either current exogenous, lagged exogenous, or lagged endogenous variables. The y vector is the set of the g endogenous variables, and the z vector here is a vector of the predetermined variables. This is the structural form of this set of equations, but a lot of times we'd like to rewrite the systems such that we only express the endogenous variables y1, y2 through yg as a function of only the explanatory variables. And the way to do that is given here. This beta matrix, the matrix of coefficients of the endogenous variables, has to be a square matrix, which means we can take its inverse. And then when we multiply that by the matrix of coefficients of the explanatory variables, we get this reduced form equations, which has a special name called analytically derived reduced form equations. And I'll say more about that a little bit later on. And here we can replace the nonlinear combinations of the coefficients of the endogenous variables with the coefficients of the explanatory variables as given in the gamma matrix with another matrix here, pi. So pi corresponds to the reduced form coefficients. Beta and gamma are the structural parameters. And this issue here leads us to an issue called identification, which I'll also talk about a little later as well. And the reason we like to go with analytically derived reduced form coefficients, because these are the marginal effects or the change in the endogenous variables due to unit changes in any predetermined variable. And we'll make that point more clear throughout the lecture. So how do we know if we have a multiple set of equations if the system is truly simultaneous? The key to that answer is to take a look at the matrix of coefficients associated with the endogenous variables in the system. And we've called this matrix beta here, as we did in the previous slides. If we went back, here's our beta matrix here. If the beta matrix turns out to be a diagonal matrix, well, then the equations, they're multiple in nature, but they're not jointly determined or simultaneous. They are seemingly unrelated. And of course, we've had a lecture already with seemingly unrelated regression models. If the beta matrix is either upper or lower triangular, meaning, and here's an example of an upper triangular matrix, if all the coefficients of the beta matrix above the diagonal are 0, and at least some of the coefficients, or at least one really, coefficient associated with the beta matrix below the diagonal is non-zero, the system's recursive. Now, if beta is neither diagonal nor triangular, we speak of a simultaneous equation model, or in general, a general interdependent system. So by default, if you're looking for the beta matrix, if you've specified the matrix of coefficients of endogenous variables, which has to be a square matrix, if the beta matrix again is not diagonal, and if the beta matrix is not upper or lower triangular, then we have a simultaneous equation model. Now, I mentioned this issue just a few slides ago, but it's a key issue here, one called identification. And the key about identification is the following. And by the way, there's a seminal paper written in 1927 by Elmer J. Working that deals with precisely this issue. So this issue was first recognized by Working about 93 years ago. Remember the pi matrix here, which is equal to, or the matrix of coefficients from the reduced form equations. And these coefficients turn out to be a nonlinear combination of the coefficients associated with the simultaneous system. The beta matrix here, that is the coefficients associated with the endogenous variables, in the gamma matrix. Here, the coefficients associated with the current exogenous, lagged exogenous, or lagged endogenous variables. By the way, I just noted an error here. Beta should be inversed and gamma should not be, so make that correction in your PowerPoint slide and I'll do the same thing. So the problem of identification is, do we have enough information to enable the determination of the structural parameters, these, from just the reduced form parameters? Now, if there's no way to determine all of the elements of the beta matrix and the gamma matrix from pi, then we call this system under-identified. If there's exactly one way to determine all the elements of beta and gamma from the reduced form coefficients, we call that issue just identified. And if there's more than one way, often the typical case, to determine elements of the structural parameters from the reduced form parameters, then we call this an over-identified system. And the general situation in most econometrics is over-identification. You want to stay away from under-identification. Now, how do we ensure that the identification issue will be met? Well, we're going to have other conditions here known as rank and order conditions, and I'm going to discuss each of these in turn, coupled with some examples to give you a feel for this determination. So let's talk about order conditions. Order conditions are necessary but not sufficient conditions to warrant identification. And what we're going to be looking at here is the number of predetermined variables excluded from the given equation must be at least as large as the number of endogenous variables included in that equation less than 1. So order conditions, similar to rank conditions, we're going to have these conditions holding for each equation in the model. And what we need to do is to count the total number of predetermined variables in the whole system, and then figure out how many predetermined variables have been excluded from the given situation and compare that to the number of endogenous variables included in the particular equation minus 1. So if the number of predetermined variables excluded from the given equation is at least as large as the number of endogenous variables included in the equation less than 1, then we have met the order condition. Now, rank conditions are more difficult, but yet they are necessary and sufficient. So in order to satisfy this condition, you must find at least one non-vanishing determinant of rank capital G minus 1, where capital G equals the total number of endogenous variables in the system. Excluded, we must find at least one non-vanishing determinant of rank G minus 1 of endogenous and predetermined coefficients, excluded from the structural equation being considered but appearing in the other G minus 1 structural equations of the model. It sounds difficult to understand, but we'll follow up with some examples. So let's put some meat on the bones of this terminology. So let's use capital H to adhere to the total number of predetermined variables in the system. Capital G, the total number of endogenous variables in the system. Little h, and H and G are not going to be dependent on equations because they're dealing with the total number of either predetermined or endogenous variables in the system. But little h and little g here should have a subscript I corresponding to the particular equation under consideration. So little h is the number of predetermined variables in the particular equation being considered. Little g is the number of endogenous variables in the particular equation being considered. So for order conditions then, to be satisfied for each equation I, capital H minus little hi represents the number of predetermined variables excluded from the equation under consideration. And that has to be at least as large as the number of endogenous variables, little g, in the ith equation minus 1. If we have this situation down here, where capital H minus h sub little I is less than g sub I minus 1, well, this corresponds to under-identification, the middle condition over-identification, and the top condition just identified, okay? So if some structural equations are under-identified, then it's not possible to estimate all their structural parameters from the reduced form parameters. And when that is the case, we need to make adjustments in the model. And also an important statement here, the order condition is necessary. That has to be achieved or fulfilled if identification is to be achieved. But just because the order condition is met, that doesn't necessarily guarantee that we are fulfilling the identification situation. So in that case, we must appeal to the rank condition. And the rank condition, as stated before, a necessary and sufficient condition for identification. And in this case, what we need to do, we need to find a non-vanishing determinant of rank capital G minus 1. So capital G, if we have two equations, the non-vanishing determinant would be of rank 1. If we had capital G being equal to 3, we need to find at least one non-vanishing determinant of rank 2. And what we need to do is to find the non-vanishing determinant of the endogenous and predetermined coefficients that are excluded from the structural equation being considered, but appearing in the other G minus 1 conditions, or equations of the model. When the rank condition is fulfilled, we know that the structural equations with which we are dealing are going to be identified, okay? The difficulty is the fact that we have to deal with non-vanishing determinants of various ranks. And if we know which parameters in each equation are non-zero, then we're in a position to justify the identification issue through the rank condition. The problem is we really don't have this information in advance until after we estimate the parameters in the system. So that's the rank condition here. And I think we probably should just go ahead with an example. So here's an example of a simultaneous equation model. And we'll verify that that would be the case. So we have three endogenous variables. All the equations are stochastic, y1, y2, y3. The predetermined variables, besides the constant term, are z1, z2, z3, z4, z5, and z6. So in addition to the intercepts of each equation, we have up to 6 predetermined variables in the system, z1 through z6. Now notice in each equation, we don't have to have, and in fact, none of these equations has all predetermined variables in each equation. And also note that we have y1 on the right-hand side of y2, and we have y2 on the right-hand side of y3. And in y1, we don't have y2 or y3. and we don't have y3 in the second equation, and we don't have y1 or y3, or we don't have y1 in the third equation. So let's consider rank and order conditions. First of all, before we do, what you should attempt to convince yourself of is verify that this system is in fact simultaneous. So what you would do is formulate a 3x3 matrix of coefficients associated with the endogenous variables. And when we are able to do that, you'll note that that coefficient matrix is neither diagonal nor upper or lower triangular. Hence, the system is going to be simultaneous. Now let's check on identification issues. First of all, what are the number of predetermined variables in the system? That's capital H. Here my answer is 7. Why is it 7? Well, we have 6 z's and the intercept counts as the other one, so that's 7. So how many predetermined variables do we have in the first equation? 3. How many in the second? We have 1, 2, 3, 4, and in the third equation we have 1, 2, 3, and 4. Oh, by the way, I may have misspoken. In the second equation, notice that y1 and y3 appear in y2, but that doesn't exist in the first equation, and it doesn't exist in the third equation. So back to our story about identification. In the first equation, capital H is 7, but what we need to do is to subtract off the number of explanatory variables in each equation. So in this one, the number of explanatory variables or predetermined variables should be 3. So if we do that, and here's another error on my part, this first equation should have 7 minus 3, which means there are 4 exogenous variables excluded from the first equation. What are they? Well, Z3 is not included, Z4 is not included, Z5 is not included, Z6 is not included. So how many endogenous variables do we have in the first equation? 1. So if we have 1 endogenous variable, equation 1, this should be 7 minus 3 is greater than 1 minus 1. And the same thing for equation 2. The number of explanatory variables excluded from the model is really Z5 and Z6, Z5 and Z6. That would mean 2, and that has to, and how many do we have in the way of endogenous variables in the second equation? Well, we have 3. So in this case, we should have 7 minus 1, 2, 3, 4, 7 minus 4 being greater than 3 minus 1 or 2. So this 2 should be a 3, this 3 should be a 4, and in the third equation here, and in the third equation, the number of explanatory variables excluded, Z2 is not included, Z3 is not included, Z4 is not included. So there's 3 variables that are predetermined that are excluded from the third equation, but that is larger than 2 minus 1, the number of endogenous variables. So in each case, based on the order conditions, and assuming one can count, you should be able to verify that in this example here, we have an over-identification. Now remember, this should be a 3, that 2 should be a 3, that 3 should be a 4, and also this 3 should be a 4, my error. But in each of the cases, we still show that each equation in the system is over-identified. So what are we doing here to look at rank conditions? The first thing I would do is to consider columns of variables in the model. So we have y1, y2, y3, and then each of the 7 predetermined variables, z1, z2, z3, z4, z5, z6, and z7. And what I would do is write their coefficients accordingly in each of these. So if we go back here, if we were to translate each of the y's to the left-hand side of the equation, and here you'll get the 3x3 matrix, beta matrix that I was talking about. And you can see right here, if you just concentrate here, that notice that the beta matrix 3x3 is neither diagonal nor upper nor lower triangular. Now, if it were the case that beta 2, 3 were equal to 0, we would have a recursive system. Or if it were true that beta 2, 1 and beta 3, 2 jointly were 0, we would also have a recursive system. So we're assuming that at least one of these coefficients, beta 2, 1, beta 2, 3, or beta 3, 2, would be non-zero, okay? Now, what are these coefficients? Well, these coefficients represent the coefficients associated with the predetermined variables. So we have gamma 1, 1, gamma 1, 2 associated with z1 and z2, but the rest of them are 0. So this should be gamma 1, 1, gamma 1, 2, the rest of 0, and here's the intercept. By the way, there shouldn't be negative signs here. These should be positive. These coefficients should be positive. And what we need to do, according to the rank condition, so if you take a look at equation 1, what you want to consider is the set of coefficients, both from the endogenous variables and the predetermined variables that are excluded from the equation, but appearing in the other equations. So notice, what coefficients are excluded from equation 1? Well, the coefficients associated with y2 and y3 are excluded, and the same for z3 through z6. So when that happens, we get a determinant here that, or we get a set of coefficients. What's being considered here is the set of coefficients that are excluded from equation 1, but appearing in other equations. Now, what we need to find is a non-vanishing determinant of rank 2 associated with that, y2, because capital G is equal to 3. And so what we need to consider from these coefficients now that have been excluded from equation 1 but appearing in equation 2, a non-vanishing determinant of 2 by 2. Well, how many of them are there? Well, we have 6 columns here, taken 2 at a time, and the binomial coefficient 6 choose 2 equaling 15. I'll do the details here in a moment. And in equation 2, notice there's only 3 columns here, all corresponding to the z's that are excluded from this equation but appearing in the other equations. So what we have to consider then is non-vanishing determinant of rank 2 from this set of coefficients. Well, we have 3 columns, taken 2 at a time, we get 3 conditions. And then the last, we're also considering all the coefficients excluded from the third equation, but appearing in the other equations, which means we have to consider these 2 coefficients, these 2 coefficients, these 2 coefficients, these 2 coefficients, and putting together this submatrix. And once we have the submatrix, we need to find a non-vanishing determinant of rank 2, and there's 6 of these, 4 taken 2 at a time. So if we look at the first equation, one 2 by 2 matrix we can make from that submatrix would be this one: 1, negative beta 2, 3, negative beta 3, 2, and 1. And when we do that, notice we get this matrix, and what we want is that determinant, which happens to be 1 minus beta 32 times beta 23, in this case, not to be equal to 0. Well, when will that happen? We can't have the product of beta 32 and beta 23 equaling 1, otherwise the rank condition would not be met. So we're going to have to do the same thing for each of the 15 possible ways we can form non-vanishing determinants of rank 2. Now we only need one. So in this case, based on the second 2 by 2 matrix, what we need to find is either gamma 2,3 or beta 3,2 not equaling 0. The third, beta 2,4, beta 3,2 not equal to 0. Fourth and fifth, either gamma 3,5, gamma 3,6 not equal to 0. And so forth. Now notice in the 10th case, the determinant is 0. Nothing we can do about the parameters, and the 15th as well. But in all other cases, to be a non-vanishing determinant of rank 2 depends on certain coefficients, either the gammas here or the betas here, or the fact that the product of 2 beta coefficients can't be equal to 1. If any one of those is satisfied, then equation 1 is satisfied with the rank condition. For equation 2, there's only 3 possibilities. And in this case, we must have gamma 1,1 not equal to 0, or gamma 3,5 not equal to 0, or gamma 3,6 not equal to 0. And if we have any one of those conditions, then what we have is the rank condition being satisfied for equation 2. Remember, this is done on an equation by equation basis. And for the third, we have 6 possibilities. So there's a lot of work, and that's just for 3 equations. Suppose the number of equations is much larger than 3, well then it becomes much more difficult to come up with conditions to ensure the rank conditions. But no matter what the number of equations, one can easily use the order conditions to determine identification. So it's good practice with this example now to make sure that you go back with this example and understand the use of this example with order and rank conditions, okay, to deal with the issue of identification. Now, the next major issue in simultaneous equation models happens to be, how do we estimate the structural parameters? And there's many ways to go. What I've listed here are probably the 5 most common. The first is simply use OLS, or correction for serial correlation, in each equation. The second and third involve alternative estimation procedures known as 2-stage and 3-stage least squares. And I'll describe the technique here momentarily. The nice thing about 2- and 3-stage least squares, one does not have to impart a distributional assumption about the error term. The last 2 deal with limited or full information maximum likelihood, but of course, in order to use maximum likelihood procedures, one must specify the distribution of the error terms, and typically that distribution, and not surprisingly, is often going to be a normal distribution. So what happens here with the use? Let's talk about the estimation here with this particular example. We have 2 equation systems, supply and demand. There could be an identity or an equilibrium condition that suggests that at equilibrium, Y1 must be equal to Y2. And if you'll notice here, you should be able to verify that we, contingent on certain on the estimates of the coefficients of beta 1, 2 and beta 2, 1 that we do have a simultaneous system. And notice we, apart from the intercept term, which is C1 naught and C2 naught, we have 4 predetermined variables, Z1, Z2, Z3, and Z4. And based on what we did last time, you should be able to use the order conditions to verify that this system is either just or over identified. And you should be able to use the rank conditions to determine if the system is over or just identified. And in the case of the rank conditions, all we need to do is to find a non-vanishing determinant of rank 1. So what you should do is apply the rank conditions here just to justify the fact that this system is over or just identified. Now, to estimate this, well, if we used OLS to estimate that, the problem is a potential endogeneity between the error term U1 and Y2, or the error term U2 and the error term Y1. While OLS can be used if, in fact, the error term is going to be correlated with Y2, and if the error term U2 is going to be correlated with Y1, then the coefficients for beta 1, 2 and beta 2, 1 are going to be biased and inconsistent, meaning the bias does not disappear even if our sample size is large. So what might you do? Well, we talked about the use of instrument variables earlier when we talked about the Hausman test. In this case, we have readily available instruments. So the instruments, as it turns out, are going to be all of the predetermined variables in the system. That is the intercept, Z1, Z2, Z3, Z4. So in order to eliminate the potential bias, in the first stage, what one should do is regress each endogenous variable as a function of all predetermined variables. And that would mean a regression of Y1 as a function of the intercept, Z1, Z2, Z3, and Z4. What do we get out of that? Well, we'd like to see a fairly good fit, and then take the predicted values for Y2, and instead of using the actual Y2 variable, use the predicted variables from Y2 from the first stage, and then run OLS again. Because as the sample size gets bigger, the correlation of the error term with the predicted values of Y2, based on the use of instruments, will go to 0. And that is called two-stage least squares. And here in the second equation, we take the predicted values from of Y1 from the first stage, and then replace the actual Y1 with those predicted values and run OLS again. That's called two-stage least squares. The problem with either OLS or two-stage least squares, and two-stage least squares at least mitigates the biased issue in parameter estimation. Neither OLS nor two-stage least squares takes into account the correlation of the error terms across equations. Now, when we do that, after you've done the two-stage least squares estimation, you would get the residuals. The residuals then, we would get the correlation of the residuals with U1 and U2, and taking that information into account, apply an estimator much like the estimator that we would get from seemingly unrelated regression, but we call that three-stage least squares because we have right-hand side endogenous variables. So three-stage least squares is a full information estimation technique because it not only mitigates the potential bias in the right-hand side endogenous variables, but we take into account additional information, typically the correlation across the error terms. And limited information maximum likelihood estimates the same thing with the use of maximum likelihood techniques, still using the predicted values from Y1 and Y2 from the first stage, and then using a distributional assumption for the error term to carry out the estimation. So now if we rewrite our system in terms of a matrix representation, this is the beta matrix, and notice in order for this to be a simultaneous system, beta 1, 2 and beta 2, 1 both have to be non-zero. Have to be. If either one of these were zero, then we would have a recursive system. If both were zero, we would have a seemingly unrelated regression model. And they're easy to spot, that is, seemingly unrelated regression models, because there's no right-hand side endogenous variable. That's consistent with a diagonal matrix of the estimated coefficients, okay? Now, the deal here is, and the reason we go and write the system in this way is, let's talk about getting shocks or impacts of each of the predetermined variables on the endogenous variables y1 and y2. The common mistake here is to assume that the coefficients associated with, let's just focus on Z1, tau 11 here, or T11, that's the marginal effect of a unit change in Z1 on Y1. Well, why isn't that the case? Well, if Z1 changes by 1 unit, there will be a change of tau 11 in Y1, but if tau 11 is the change in Y1, then there's going to initiate a change in Y2, and if there's a change in Y2, that'll initiate another change in Y1, and so forth. And the other thing to consider is you may make the mistake, but don't do that, that an impact of a change in Z3 and Z4 would have no impact on Y1 because Z3 or Z4 doesn't appear on the right-hand side of Z1, or alternatively, Z1 and Z2 have no impact on Y2 because they don't appear on the right-hand side of the supply relationship. Well, that's not the case because Y1 and Y2 both involve Z1 and Z2 as well as Z3 and Z4. So to actually get the full flare of ultimately what is the analytically derived reduced form, if you were to write out the matrix in this fashion and then do a little matrix algebra on slide 33 here, at the end of the day, what we get is a set of analytically derived reduced form equations. Now, to be analytically derived, what does that mean? First of all, we've eliminated y1 and y2 from the right-hand side of each equation. And notice now each equation has associated with it each of the predetermined variables as well as a constant. And the other thing to consider is that the coefficients associated now with Z1 are a nonlinear, or Z2, Z3, and Z4 are nonlinear combinations of the coefficients associated with the coefficients of the endogenous variables and the coefficients here associated of the predetermined variables. You'll get a chance to work on this problem in problem set number 4, dealing with a data set here called ag food. I believe it's problem number 6 that I've asked you to, or maybe number 5 to deal with that. So you should be able to write what the analytically derived reduced form equation, in the case of 2 equations anyway. I wouldn't expect you to do that for more than 2. But if you were not good with matrices, how can you arrive at that? Well, if we come back here, you can simply algebraically substitute y2's expression here, collect the common terms, and then be in a position to calculate the analytically derived reduced forms. Similarly, down here, replace y1 with this expression, collect common terms. Notice when you do that, Although Z3 and Z4 don't appear in the first equation, when you bring the expression for Y2 up here, Z3 and Z4 now appear, and the same is true when you replace Y1 here with its structural system. So you needn't necessarily be a wizard in matrix manipulation in order to do that, just algebraic substitution. So at the end of the day, you know, these are important. Why are they important? Because they represent the nonlinear combinations of the coefficients, structural coefficients associated with the predetermined variables and the coefficients structurally of the endogenous variables. And the expressions represent the marginal effects for this system. So that's how we talk about then the marginal effects or changes in each of the predetermined variables on the respective Y1 and Y2. We can convert these to elasticities just as we had before. Everything is business as usual. By the way, how do you forecast with this system? Well, we use the analytically derived reduced form. So conditional on forecast of Z1, Z2, Z3, and Z4, and the estimated coefficients of the betas and taus, we can then put together an expression to allow us to forecast. So we accomplish the same three outputs of any regression analysis. One, how do we determine which variables are statistically influential in affecting Y1? Well, that's just based on the estimated coefficients and their p-values. How do you get the correct marginal effects? That's done through the analytically derived reduced forms. How do you get forecasts? Also done through the analytically derived reduced forms. So let's delve a little bit further in analytically derived forms. I'll give you a couple of examples, and then we will put to bed this lecture here dealing with multi-equation models that are simultaneous, very important in actual econometric practice. Now, you know, the key to analytically derived reduced forms is what is the makeup of the set of predetermined variables. They could all be current exogenous variables, or there could be some lagged exogenous variables, or there could be some lagged endogenous variables. And this issue of further delving into the analytically derived reduced forms was put together way back in 1962, 58 years ago, with the work of Henry Tile and Boot in the review of the International Statistical Institute. Here's a picture of Henry Tile. You pronounce his last name T-I-L-E, although it's spelled T-H-E-I-L, one of the prominent econometricians and economists in our lifetime. So what he suggests that we do here is to break up the set of endogenous or predetermined variables into three groups of variables. If you have lagged endogenous variables, the matrix A here corresponds to the coefficient matrix of the lagged endogenous variables. This has to be a square matrix. You could also have a matrix or of current exogenous variables, and the beta matrix here, which doesn't have to be a square matrix, comprises the coefficients of those. And you could have lags of current or lags of exogenous variables, in this case a one period lag, and then the C matrix is the resulting coefficient matrix. Now, why do we want to do this? Well, noteworthy characteristics. Here, this allows us to take a look at how changes in X's how changes in predetermined variables vary over time. And the only way that can happen is if we include either lagged exogenous or lagged endogenous variables. Now, each equation doesn't have to contain all endogenous and exogenous variables lagged. That is, some of the elements of A and C are 0. But if you're interested in tracking changes in exogenous variables through time, then the matrix A or C or both must not be 0 or null matrices. If they happen to be 0 matrix, no need for this term, no need for this term. And what we've just described, the B matrix with our simple example, would be the system of analytically derived deduced forms based on current exogenous variables. But sometimes the right-hand side or predetermined variables could be lagged, or we can have lagged endogenous variables. So how does this work? Well, if we wanted to consider how changes in any exogenous variable affect any dependent variable contemporaneously, the expression is to simply say, look at the coefficient matrix B here. That gives a contemporaneous change in Y due to a unit change in X. And we call those impact multipliers. Now, let's suppose we have the A matrix and the C matrix in play. That is, there's a 1 period lag of exogenous variables, or there are lags, 1 period lag of endogenous variables. If that's the case, if you look down here with some mathematical manipulation, to look at changes today, 1 period ahead on the dependent variable, we get the expression A, B plus C. So once you've identified the A matrix, the B matrix, and the C matrix, you're able to carry out what the impact of a unit change in X today would be on each of the endogenous variables 1 period ahead. And you'll get similar expressions 2 periods ahead, or in general, S periods ahead. So this allows you to measure the net effects of changes in exogenous variables on endogenous variables, in general, S time periods later. Now again, remember that some lagged endogenous variables have to be included in the model, or it will not be possible to access any of the interim multipliers, because if this is the 0 matrix, ds is going to be equal to 0, and we're forced to only look at the B matrix. Now, if we have lagged endogenous variables in the model and we want to add up their cumulative effects, much like we did when we were looking at polynomial distributed lags, provided stability conditions hold, we can get a general expression for what the long run or total multipliers would be. And this is the expression for the total multipliers. So all of this work was the work of Henry Tile and Boot, and typically plays some handsome dividends for us if we want to trace the impacts of changes in exogenous variables on endogenous variables through time. I'll have an example to illustrate that. So in sum, you see, it's important to get multipliers from simultaneous equation models, milking as much information as you can from the system. So in addition to looking at the correct marginal effects, being able to forecast to identify which variables are significantly influencing the various endogenous variables, we can seek out the marginal effects that might change from one time period to the next. But in order to do that, in order to consider interim multipliers and total multipliers, we're going to have at least some lagged endogenous variables in our model, or some lagged exogenous variables in our model. So here's an example to illustrate all of that. It's an actual example. The demand and price markup functions for canned cling peaches and fruit cocktail French and King. I believe it's the old Western Agricultural Economics journal, 1986. So there are 4 dependent variables, and now notice we can also consider natural log expression. I'm not going to go into great detail, but QMRN, QMFN, PPR, which is the price at retail of peaches, PPF, the price at the farm level. So we have 4, structural equations here. The rest of the variables happen to be predetermined. Notice no lags, though, no lagged dependent variable, no lags of exogenous variables. So the only thing we will be able to consider are impact multipliers based on the previous discussion that we had concerning the work of Tile and Boot. Now, again, if you write out what the square matrix is for this system of 4 equations, here it is, and notice that we have the possibility here of a system here that's recursive and not truly simultaneous. But nevertheless, everything that applies with simultaneous equation models holds true. So you see, this is a lower triangular matrix, which means the system constitutes not only a simultaneous system, but a subset of that, a recursive system. And if it happens to be the case that beta 1, 2 and beta 2, 1 are both 0, then we have a seemingly unrelated regression model. So how do we deal with this? So I'm going to talk about, and if you want the data, I've made the data available so you can verify this not only with SAS that I'm using, but with other packages like eViews, R, or Stata, as many of you are. And the actual article here, you can go to the Western Journal of Ag Economics, as I mentioned, 1986. So it's a peaches example. What I'm doing is reading in all of the data, and here are various ways to specify what the data are with transformations. And we can use OLS to estimate this. You can verify that yourself. Now, let's suppose we wanted to consider, getting 3-stage least squares estimates. How would we do that? Well, in SAS, we would use Proc-Syslin, system of linear equations, much like we did for seemingly unrelated regression models. This is the estimation technique, and here I wanted to preserve the estimated coefficients, and I'm going to call the preservation of those structural coefficients peaches 3-stage least squares. Now we have to specify 2 additional statements. We have to provide a list of endogenous variables, and as I said, there are 4. And now we have to specify a list of instruments. This is the list of predetermined variables, which also includes an intercept. But the intercept, at least in SAS, is included by default. So in this particular case, you see, this, apart from the intercept, gives us the list of all predetermined variables in our model. So in this case, we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and when you include the intercept, 17. So capital H, if we went back to order conditions, is equaling 17. Capital G is 4. But we can verify the rank and order conditions in each of these. At least the order conditions, the rank conditions, you would have to find at least one non-vanishing determinant of order 3 by 3, and I'm never going to do that to you. So in SAS, to set this thing up after these 2 statements, just specify the equation. And here I'm also retrieving the predicted values that we get from the use of 3-stage least squares. So if you look at the first equation, here's a right-hand side endogenous variable. So what would you do? The first thing you would do is to, based on a regression of LPPR as a function of all these instruments, replace LPPR with their predicted values, run that equation again, that's two-stage least squares, and then consider the correlation of the error terms among the four other equations to get the three-stage least squares estimates. That's why this instrument statement is important, to allow SAS or other packages note what instruments are being used in order to mitigate the possibility of an endogeneity problem dealing with the right-hand side endogenous variables. The nice thing about Simlin is that it will also allow you, using the estimated coefficients, to actually come up with an expression associated with the analytically derived reduced form equations. In our simple example of 2 by 2, we just algebraically replace that. That becomes a lot more cumbersome when we move away from 2 equations as we have here in the case of 4. So in this particular case, this function here, or this procedure, allows us to, using the estimated coefficients for three-stage least squares, come up with analytically derived equations for each of these 4 variables. And we need a statement here called endog. Yes, that's right. And then, given the fact that we only have current exogenous variables, we just simply use the word exogenous, and this is the same list of predetermined variables, currently exogenous variables, that we had in our instrument statement. So at the end of the day, each of these 4 endogenous variables will be written as a function of these 16 or 17 predetermined variables. So if we go through some of the slides, I'm not going to bother with OLS. You can do that. Now, in order to get three-stage least squares, though, we got to do two-stage least squares. So Syslin allows you to look at the two-stage least squares estimates. And the key here is that even though this says LPPR, this is really not the actual endogenous variable. It's the endogenous variable replaced with predicted values when we ran a regression of LPPR as a function of all predetermined variables in the system. And as you can see here, all variables are significantly driving the dependent variable LQMRN. And here, for the second equation, good fit, all variables are statistically significant again. And once again, this right-hand side endogenous variable has been replaced by predicted values from the first stage. And by the way, SAS does not provide those first stage estimations, but they're certainly easy to retrieve. I'm not sure what other packages actually do. Here's the third equation. Here's the fourth equation. So we were actually able to mimic the results in that Western Journal of Ag Economics paper written in 1986. But now to get the three-stage least squares, we have to, similar to what we did in the use of seemingly unrelated regressions, get the variance covariance matrix of the residuals from two-stage least squares, not OLS, convert that to correlations, and then use this information in another round of estimation, and that's how we get the three-stage least squares estimates. And the fact that we have non-zero cross correlations of disturbance terms means that three-stage least squares, again, a full information estimation technique, adds information beyond OLS and two-stage least squares. Now, when we do that, we get a new set of parameter estimates, and here they are. And if we were to compare these standard errors from three-stage least squares from the standard errors of two-stage least squares, these have to be smaller, or at least not larger. And while we didn't talk about rank conditions, a fellow by the name of Bosman, who used to be at Texas A&M University provided a test for over-identifying restrictions. The null hypothesis is that each equation is not identified, and in this case, you would like to reject the null hypothesis just as we've done here. I can provide details on that test, but all I wanted to share with you is that SAS actually allows us to deal with that test. And what you need as an option is the option over ID. I'm not sure if other packages, whether they be Stata or eViews, allows that to happen. Here's Robert Bosman. And, you know, we do that for each equation. And we find that each equation is over-identified. We get the three-stage least squares estimates. And we also now are able to get goodness of fit associated with that using a similar technique that we get when we use seemingly unrelated regression, although with eViews, you don't necessarily have to do this because eViews will provide the goodness of fit, and likely the same will be true for Stata. So we get all of these, and of course you can verify the information when you make the runs yourself. So here's a summary for each equation. Here's the LQMRN equation, natural log. So in this particular case, natural log here, well, now these coefficients, natural log, are likely to be elasticities, but you have to be careful because we need to retrieve the correct marginal effects, and we can only do that with the analytically derived reduced forms. And the other thing to note here is that there's a definitive reduction in standard error attributed to the three-stage least squares procedure. And you'll see that in each equation. And it is also possible to get Durbin-Watson statistics printed out with this. Now, with the Simlin procedure, this allows one to, based on the estimated coefficients from three-stage least squares, get to, and SAS calls this reduced form, but to be perfectly correct, you need to have the adjective analytically derived reduced form. So in this first equation, you know, LQMRN, if you were to write this thing out as 0.383 times LTDIN minus 2.2085 times D7 plus 0.0766 times T14, et cetera, because there's 17 of these variables. These coefficients are the impact multipliers and the correct marginal effects. And if we went back here, given the fact that this is a dummy variable, we can use the same trick that we had before to talk about how much of a reduction in QMRN occurred after 1970 relative before 1970, because the dependent variable LQMRN happens to be a log. And this is also log, so this is actually the elasticity here. A 1% change in LTDIN generates a 0.383% change in LQMRN. And how would we forecast with this? Well, if we conditionalize the forecast by providing values of the exogenous variables here, and here, using the analytically derived reduced forms, we can generate forecasts. Now, let's suppose, because in this example, to round out this rather lengthy lecture, suppose that we now introduce lagged endogenous variables in order to incorporate some dynamics, not out of the question for sure. The question then is, when you have the dynamics, if we were to shock the system, will it return to equilibrium after some time, and how would it return to equilibrium? So the key here is to focus on a non-zero A matrix, the matrix of coefficients of lagged endogenous variables, which has to also be squared. So as I said, after a departure from equilibrium, will the system eventually return to equilibrium? And if that's the case, then we say the system is stable. So the eventually, based on stability conditions, means that the endogenous variables, or the mean values of the endogenous variable, eventually settle down and return to an equilibrium state. But if the system is unstable, then there won't be a return to the equilibrium state. So stability conditions are going to be important when one introduces lagged endogenous variables. And how do we know if the system is stable? Again, you're focusing on this square matrix. It doesn't have to be symmetric, which means one would retrieve the characteristic roots of that matrix, whatever dimension it would be. So for a 4x4, there'd be 4 characteristic roots or eigenvalues associated with that. And all of them must be less than 1 in modulus. Now, the reason we say modulus rather than absolute value is to recognize that given the fact that we have a non-symmetric A matrix, you could have eigenvalues or characteristic roots that are complex numbers. So let's see an example here. So what we will do, you're going to have to retrieve the characteristic roots of the A matrix, and you want none of them to be greater than 1 in modulus. So for example, if we had a complex characteristic root or eigenvalue, let's say generically C plus DI, the modulus is the square root of C squared plus D squared. The first thing is you want all of these characteristic roots to be less than 1 in either absolute value or modulus. Now, if the dominant root, which determines the behavior of the system, is positive, then we have monotonic convergence. That is, the system will initially depart from equilibrium, but eventually settle down and converge. If the dominant root is negative, the system will eventually settle down, but not in a geometric decay, but the system will oscillate each period. You get a geometric decay with monotonic convergence if the dominant root is positive. But if the dominant root is negative, the system oscillates each period. And if you get a complex dominant root, that implies cycles. And to actually find the length of the cycle, you can use trigonometry to help you there. Here, in this case, using this diagram, I can look at the cosine of the angle R, which is equal to adjacent over hypotenuse. And the length of that cycle, once we determine what R is, gives us how long that cycle would last. Now, just to give you an illustration, Lawrence Klein, a Nobel Prize winner, used a dynamic system of macroeconomic equations to try to take a look at the US economy over the period 1921 to 1941. This is the Klein's model. It's known as Klein Model 1. Notice there's lagged dependent variables in the model. There are no lagged exogenous variables. Now also note that his system has identities in it as well, but only 3 stochastic equations. But since we have 1, 2, 3, 4, 5, 6, 7 dependent variables, then we have a system, a simultaneous system of that amount. In fact, the endogenous variables actually turns out to be 8 here. Consumption 1, 2, 3, 4, 5, 6, 7, 8. These are the current exogenous variables, but there are lags of endogenous variables. And here is Lawrence Klein, his picture. So we can write out the matrix just as we, or the system of simultaneous equations in matrix form. Here are the matrix of coefficients of the endogenous variables. Notice that this is neither an upper nor lower diagonal matrix, and it's upper or lower triangular or diagonal matrix, so the system is is simultaneous by default. Now, if we were to write out the analytically derived reduced forms using Tiles nomenclature, here is how we would retrieve the A matrix, the B matrix, but the C matrix is 0 because we don't have any lagged exogenous variables. So we can not only get elements of B, the impact multipliers, but we can get interim multipliers given by this expression here once we've made the determination of the structural equations. And in this example, because we only had 3 endogenous variable or 3 equations that were actually stochastic, even though there's 8 characteristic roots, 5 of them are 0, and here are the other 3. And typically when we get a complex root, they occur in what we call conjugate pairs. That is, the real and imaginary coefficients are the same, but for the sign. And if you look at the modulus here, the modulus is 0.768 for these 2 characteristic roots, and the characteristic value for the other lambda 1 is positive, but the dominant root comes from complex numbers. Therefore, we're in a position to calculate the length of the cycle, because we know that the system will converge after it is shocked and it'll move back to equilibrium, but after a period of time, and that period of time will correspond to cycles. And it turns out that Klein was the first to suggest that the economy actually is very similar roughly every 16 years once we depart from equilibrium. All because of the econometrics here. Now, to finalize this lengthy lecture, here's a good example that came out of Pendyke and Rubenfeld, and I've also provided the data for it. Notice there's 4 equations, 4 endogenous variables: GDP, consumption, IIN, INV. GDP is deterministic. It's an identity. And we have each of the setup here for the remaining 3 stochastic equations, but notice in each stochastic equation there are lagged endogenous variables, okay? So this system is due to dynamics. And if you take a look at the matrix of coefficients here associated with endogenous variables, the only way this thing can be recursive is if beta 3, 2 equals beta 4, 1 equals beta 4, 2 is equal to 0. Otherwise, the system is simultaneous. Here are the variables, both exogenous and endogenous, and one can go ahead, at least for the 3 stochastic equations, use order conditions and rank conditions to verify that. And even though GDP, for example, is a deterministic equation, it does play a role in the rank conditions, meaning we'd have to find at least one non-vanishing determinant of rank 3 of all coefficients that were excluded from the C equation, and that would be the GDP, IIN, INV, G, INR, IR. That would be a rather complex and formidable tasks, you know, based on the formulation of these various submatrices. So I'm not going to ask you to do that, although I just took a look at certain determinants here just to show you what the identification issues would be with the rank conditions, or what the coefficients would have to be. So we better have gamma 1, 2, for example, for I and V not to be equal to 0 for it to be identified. And based on this one, either gamma 1, 3 or beta 3, 1 not being equal to 0, or the product of beta 2, 4 times beta 3, 1 not equaling -1. I will not ask you to do this on any final exam, but I just wanted to be thorough here. So I provided the data. You can go ahead and verify this, but again, what I'm planning to do, similar to what we had before, is to use proxyslin. And once again, we need to specify the 4 endogenous variables, yes, even the identity involving GDP, and the list of all predetermined variables in the model. But don't forget, the predetermined variables are not only the current exogenous variables, which would be 1, 2, 3, 4, 5, 6, 7, but also, and there's 1, 2, 3, 4, 5, 6, 7, but also the lags of the endogenous variable, lag C, lag IIN, lag INV. And we simply write out the equations. Here's the over ID deal based on Bosman. I didn't go into detail on that. That's another way to verify the over identification issues. And now to get the analytically derived reduced forms, because now we have the added dimension or complex element here dealing with lagged endogenous variables, we get the same setup here, endog, the 4 endogenous variables, the 1, 2, 3, 4, 5, 6, 7 exogenous variables, but now we need to specify lagged variables. So we have lagged, and then the lag of C, which is a lag of C, and 1 means of order 1, IIN, lag of IIN of order 1, etc. So once we have that, and here, how many interim multipliers do you want, given the fact that these correspond to quarterly data? I let 4 being equal to not only the contemporaneous period, but after 1 quarter, 2 quarters, 3 quarters, 4 quarters, and then find the cumulative or total multiplier as well. SAS will provide all of that. So if you're doing this, you want to verify that you get the same means procedure. And even though we have serial correlation, I'm just asking to put that on the back burner for right now. And we're going to use 3-stage least squares. In order to do that, we got to get 2-stage least squares first. And now we get and the reason that we are estimating 3 equations, because one of them is an identity. And notice the off-diagonal non-zero correlations, which means we're going to get some gains in efficiency with the use of 3-stage least squares. So here are the 3-stage least squares estimates, and based on these p-values, you can determine which variables are statistically important in affecting consumption, or IIN, or INV. And at the end of the day, we can summarize this for each equation, and notice once again the gains or the lowering of standard errors for 3-stage least squares compared to 2-stage least squares, okay, for each equation. So we've summarized that. And then we need to get, based on the Simulin procedure here, the analytically derived reduced forms. So we need to get the inverse of the coefficient matrix for the endogenous variables to play a role. And now we get the reduced form for the lagged endogenous variables. So if we were to write this out, C here would be equal to, well, would have part of it in it, 0.5503 CT1, but not the other lags. In the GDP equation, we'd have lags of lag C, IIN, and INV, And the same thing would be true for IIN and INV. And for the B matrix, you get the reduced form set up for exogenous variables too. So based on the Proximlim procedure, you're in a position to capture the analytically derived reduced form here by just, the coefficient times the relevant variable listed at the top here, and writing them out. Now the interpretation is, if we wanted to see unit change in RS, what does that do to C, or unit change in wealth, or unit change in TR, or unit change in YD, disposable income? You can see what that contemporaneous impact will be. But you can also do that for the first interim multiplier, and the second, and the third, and the fourth, and the cumulative. So if we focus on YD, for example, the cumulative impact of a unit change on disposable income on consumption with this data, for every dollar spent today, the long run impact is 0.61. For GDP, 0.71. For IIN, 0.105. And for INV, 0.168. And you can also take a look at mapping or diagramming based on the fact that we have interim multipliers here. Here is the, the current or impact multiplier, the multiplier of 1 period, 1 quarter, 2 quarters, 3 quarters, 4 quarters down the road. And notice that the impact is diminishing in geometric fashion. Why is that? If we were to consider then the stability conditions, here is the A matrix, has to be a 4x4 matrix. Get the 4 characteristic roots. Note none of them is complex. And the dominant one in absolute value is this one, which means we've met the stability condition, but not only that, because the dominant root is positive, we can see that the system actually returns to equilibrium in dissipating geometrically. So there's a lot of information here. The other thing to note here is we can still get, once we have the various multipliers, we can convert the multipliers into elasticities, which I've actually done here. So business as usual, lengthy set of slides, but you might want to try your hand at each of these examples, particularly this last one, and see if you can come up with similar answers as I did. We don't go into great detail on the problem set. In other words, we don't consider on the problem set any lag dependent variables, but that doesn't mean I wouldn't include that on a final exam. All right, my friends, good to be with you. Be safe, be well.